Warning, the video you're about to watch contains mathematics at the level of integral calculus, also known as Calc 2. All material has an assumed prerequisite of differential calculus and a full semester course in trigonometry. A thorough review of prerequisite topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This video is meant for Calc 2 students who are going through areas underneath parametric curves. Now, the one thing you have to realize about areas and parametrics is that really it all centers around one specific equation. We happen to know from our Calc 1 and most of our Calc 2 that the area underneath a curve from x equals a to x equals b is the following, where y is the curve that we have in question here. Now, of course, that would be different if you were integrating with respect to y. If that was the case, you would have this curve that you're integrating underneath. However, when you're doing things parametrically, which we're going to do here in a moment, we want to adjust these formulas. Now, you can use either of these formulas actually. So I would like to use this example to showcase that so that you know that when you go into parametrics, you have options and quite a few. This tends to be a little bit of a tough part for Calc 2 students just because of the sheer number of options that you have. They told us we're using the parametrization x of t is equal to cosine of t, y of t is equal to sine of t, to form this ellipse. Let's go ahead and just take a look at the area formula. And I'm actually going to look at both of these because I want you to believe that you can do this in either aspect or either way. So if I was to integrate with respect to x, that is, if I were to take a look at this curve, which I should draw on this page, there we go. So having that drawn, now you can see that if I want to find the area within this ellipse, I have a few ways to go about it. I could do vertical slices here. And by the way, there's no need to do all four quadrants. You guys know at this point that all I really need to work with is the very first quadrant here and then just multiply it by 4. So I could do vertical slices or I could do horizontal slices. In the vertical slices, we're dealing with delta x's, so we are integrating with respect to x. And with the horizontal slices, we are dealing with delta y's, or in other words, we're integrating with respect to y. And again, I'm going to use this example to showcase that you can do this either way with parametrics. It's very, very nice. So dealing with the black ink here, the integral from x equals a to x equals b. Well, let's go ahead and set up our integral to go from x equals 0 to x equals 2 because, well, that's when our ellipse ends there. And then we have y dx. Now, the important thing to remember here is when you convert to time, right now we're in the world of x's and y's. When you convert to the world of time, the limits of the integral are going to change accordingly. So you have to figure out what is the time value when x is 0. The very important piece to remember here, and I should write this down off to the right-hand side. So the warning is when finding areas, and this is actually true whether you're finding areas parametrically or you're just finding areas with a function of x, always work from x low to x high. Integrate from the lowest x value to the highest x value. If you do not do that, your area is going to come off as the opposite sign or the negative of what the true area actually is because you're going in the wrong direction. By the way, if you're integrating with respect to y, you would go from y low to y high. And what this means is that when you convert to t, it can be the case that your new integral goes from t high to t low. In other words, a higher time value to a lower time value. That is perfectly fine. The area will still work out fine. What's important is that on the Cartesian coordinate system, if you're integrating with respect to x, you're going from left x value to right x value, or from lower y value to higher y value. That's critically important. So if you see right here, we are going from x left and ending up at x right. Let's go ahead and find out what time values are associated with x equals 0 and x equals 2. Well, when x is 0, then 0 equals 2 times the cosine of t. That's because x of t is the cosine, twice the cosine of t, which means the cosine of t will have to be 0, which means t itself has to be pi over 2 plus any multiple of pi thereafter. Now, if you think about this, when x is 0, that's likely going to correspond to time equals pi over 2. Let's go ahead and plot that down on our graph over to the right-hand side. If time were pi over 2, we know that the x value is going to be 0 because we just computed that. And then the y value is sine of pi over 2, or 1. That's associated with that point right there. And that's very important. Now we're going to go ahead and find out when is the x value 2. And that happens when time is 0 plus 2 pi k. So what we're going to do is let time equal 0. If time is 0, again, x is 2, and the y value is the sine of 0. So that actually is going to be 0. So we're at 2 comma 0. This is time equals 0. So the flow of this is actually this way, right? We could see that as time goes from time 0 to time pi over 2, the curve flows to the left, which is kind of weird for us. However, again, the integral should go from x equals 0 to x equals 2. That is, again, corresponding to time equals pi over 2 to time equals 0. A lot of students dislike that, but it is absolutely true. That is the direction of travel of the particle along the edge of this ellipse. Now we need to replace the y value. Luckily, we know that's sine of t. And now we replace the dx value, and we know from our Calc 1 that dx should be the derivative of x. There's x right there. So the derivative of that is negative 2 sine of t dt. So I'm going to replace this empty space right here. I already had the dt. I'll erase it just for this. And we're going to replace that space right there with a negative 2 sine of t dt. So when you look at this integral, it's negative 2 times the integral from t equals pi over 2 to t equals 0 of a sine squared of t. And a lot of, again, students initially will look at this and say, wait, it's a negative area. Nope, it's not a negative area because that negative will be canceled when we swap the limits. That's one of the properties of integrals. So let's go ahead and swap those limits. That'll be 2 integral from 0 to pi over 2. Also, you won't be able to integrate the sine squared very easily unless you use the power reduction formula, or in other words, if you use the half angle identity. So I'm going to go ahead and do that here. I'm going to move this out of my way, including the W. For some reason that didn't want to go with me. And let's substitute in the half angle identity. There we go. Now I just go ahead and factor out the 1/2 and I integrate. And we get the area is pi over 2. Now remember, that's only for 1/4 of this entire ellipse. So multiply that by 4 and you'll get that the area of the ellipse is 2 pi. Great. But what if you want to integrate with respect to y instead? What if you want to take a look at that guy? I'll go ahead and move this down so we have some room to work. First of all, if I want to integrate with respect to y, I'm going to go ahead and start at y equals 0 and go all the way up to y equals 1. So let's start there and say this integral is going to go from y equals 0, let me get the right ink here, to y equals 1 of x dy. You're adding up a bunch of x values and multiplying them by a thickness of y. Now we're going to change into the world of time because this is a parametric curve. And remember, we're only computing 1/4 of the area underneath this or within this ellipse. So at the end, we're going to multiply this by 4. But let's go ahead and do this. Now, x in this case, if you go looking up above, x is twice the cosine of t. So I'm going to insert that here. And dy, if I go all the way back up to the top here, dy is the derivative of y, which is cosine of t, dt. So I'll insert that into my integrand. Multiplying this by a cosine, I just can make that a cosine squared dt. This looks a little cleaner, but it's only because I haven't changed the limits of integration yet. When y is 0, I'll write that off to the right-hand side. Well, remember, y is equal to, let's see up here, y is equal to the sine of t. You can see it right here. So when y is 0, we have that 0 is equal to the sine of t. And by the way, we already did all this work, but I'm just showcasing kind of how you would do this if we were to have just approached this problem. But we know that the sine is 0 at any integer multiple of pi. And then we want to know what happens when y is equal to 1. Again, when y is 1, remember, y is equal to the sine of t. That means that 1 is equal to the sine of t. And we know the solution to that is that t is equal to pi over 2 plus 2 pi k. Again, it's always a good idea to plot these points on your curve to kind of see that direction of travel, but we kind of know how it's going to be. Again, time, we're going to go ahead and in this case, I'm going to let k equal 0 and I'm going to say, well, at time 0, the y value is 0. So let's see what the x value is. Remember, at time 0, the y value is going to be 0. At time 0, the x value is going to be 2. And that matches with what we drew here. I'm just showcasing the idea, how you would go about it if you had not done this already. And then remember, our other time value is time 1, so we might as well just, or I'm sorry, time pi over 2. So let's go ahead and plug that in. At time pi over 2, the y value is 1, and at time pi over 2, the x value is 0. And again, that matches with what we had said here. So in this case, if you were to integrate with respect to y, your time values are not going backwards. They're actually going from 0 to pi over 2. The drawing really helps here, right? You know that when the y value is 0, time is 0. When the y value is 1, the time value is pi over 2. So I'm going to go ahead and integrate from time 0 to time pi over 2. And we can factor the 2 out and also exchange the cosine squared for the half angle identity. You know the 2 and the 2 out, the 2 and the 1/2 will cancel. And now we can integrate. And we get to this guy right here. It looks very similar to what we had before. Plugging in pi over 2, plugging in 0, and we get the same answer as before, pi over 2, because the sine of pi is 0. Now remember, again, that's only 1/4 of the full area of the ellipse, but if you multiply that by 4, you'll get the area of the underneath the ellipse, or within the ellipse, is 2 pi. Really a cool idea that when you're integrating with parametrics to find areas, you could, if you're lucky, integrate with respect to x or y. It's totally your choice. And this is a theme when you're dealing with parametrics and areas and surface areas and stuff like that. That you can switch gears sometimes, not all the time, but sometimes. I hope this video is helpful, and I hope you are very successful in your Calc 2 class. I'll see you in another video, hopefully.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way, cause affects more than we can sometimes see. Things for what they are and work together until you feel at ease. Says, listen close, don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.